Okay, let's give you guys some practice. So here, I want to build myself an open top box. So this here is one side, this here is another side, and around the back you've got another side and another side here. And at the bottom you've got a base, a square base. So this is X and this is X. So it's an open top, meaning that you can actually put your hand inside the box and actually touch a base. Okay, so it's an open top box. The question is for a given volume, what must X and Y be in order to minimize the material needed to produce this open top box? Okay, so in the past I would give you a definite volume. So in the past I would say, oh, the volume of this box must be let's say 500 centimeters cubed. Um, but the thing is, I don't always have to give you a definite volume. It can be for a given volume. So one problem, it could be 500 centimeters cubed, or the next problem, it could be 700 centimeters cubed. The thing is, you have to somehow work it out for any given volume. Okay, so when you come to do this, just think of the volume as V, and V, once you set the problem, V is then fixed. Okay, well, anyway, what must X and Y be for a given volume? Okay, so press pause and have a go. And remember, you want to minimize the amount of material needed, meaning you've got a piece of, let's say, cardboard box here, you've got a piece here, you've got a piece here, you've got a piece here, and then you also got a base at the bottom. Okay, well, anyway, press pause and have a go. Okay, so to do this here, the volume is given by this. Okay, so the volume is given by the base here, X times X, and then you times by Y. So the volume is this. The area or the amount, or the area here, or the amount of material needed is given by this here, because X times Y, that's this thing here, and you've got 4 lots, and then you've got a square base here. Okay, so this, well, this is what you're interested in. So really, you're trying to visualize the area, the area of the box against X. So you're varying X here. So 1 minute X could be very big. Next minute it could be a small square here, meaning your box must be really tall here. Okay. Well, so really, this is what you're working with. This here is your constraint. Now, constraint means condition placed upon you which you have to satisfy at all times. So you're trying to solve this here. This here is your constraint, meaning it's a condition placed upon you which you have to always satisfy. Okay. So this is what you need to work out to solve the problem here. So from here, if you yeah, so from here, hang on. So from here, this is what you need to solve your problem. But this is your constraint here. But rewrite this as rearrange it to make X a subject here. Sorry, rearrange this to make Y the subject here. So divide both sides by X squared here. That will then give you this. Okay. Once you've got this, you can put this into here. Okay. So this here is your constraint. So you would rearrange it to make Y the subject, and then put this into here, and then you will have your formula. So you will then be able to visualize the graph A and X. So there's no, up here we couldn't do it earlier because we've got a Y here. So rearrange it, and then when you put this into here, everything on this side is in terms of X. Okay. So anyway, because you're constrained here, and then this here, rearrange it, and then put this into here. That will then give you this. Okay. And remember, V, once a problem has been set, V is fixed. V is a constant. Okay. V is fixed. So once you've set the problem, V is fixed. So hang on. So that will then give you this. Tidy this up. So A is given by this. So now notice that the area is in terms of x only. There's no y. The volume is fixed. Okay. Once you've set the problem, the volume is fixed. So now you've got area in terms of x only. So now you can visualize the graph. So you can plot your graph of area and x. So remember, x is our square here. Okay. And then, well, anyway, once you're at this stage here, you can plot your graph a versus x here. Now, remember from my section on sketching graphs, visualize this as x squared. So you've got a equals x squared plus some sort of constant here times 1 over x. Okay, so from my section on sketching complicated graphs, when x is big, it wants to do this. So when x is big, it wants to do a positive quadratic. Okay, when x is small, it wants to do a positive reciprocal. So your reciprocal looks like this. Okay, your reciprocal looks like that. So when x is big, it wants to do a positive quadratic. So it wants to do a positive quadratic. When x is small, it wants to do the reciprocal here. So it will look when x is small, it wants to do this. Okay, and then now somewhere in the middle, the two will merge together. So your graph will look something like this. Okay, but then we can't really have a negative square base, so we can pretty much forget about the negative side and just concentrate on this bit here. So really your graph looks something like this. Reciprocal, and then when it's big, it wants to do a positive quadratic. Okay, because of this bit here. So your graph will end up looking something like this. Okay, so this is a and this here is x. So you want to minimize the material needed to produce your box here. So this is the point at which we want, and so really we need to differentiate this. I will continue in the next video. Okay.